happening in our part of the world, show some examples of adaptation in the water resources and related sectors. And then I'll focus the second half on the talk more on the science of projecting future water availability and river flow characteristics, and then talk about some of the science, challenges and opportunities, and then finish off with a slide on how we go about assessing and managing these risks under uncertainty of our projections into the future. So here's just an introductory slide showing that we are, in fact, the driest inhabited continent. We got the lowest runoff per area, obviously, in the world. But when you start looking at water use, we actually have the highest daily water consumption per capita. And the reason behind that is because we grow a lot of food, agriculture, so irrigation. So we are really net exporters of water. Being a hydrologist, I think it's very useful to think about our hydrology. It is different from elsewhere in the world. So the first key point, if you got a low runoff coefficient, so less of our rainfall becomes runoff. So we have that challenge to overcome. The other one is this high interannual variability depicted by the red colors on the map at the top. So ourselves in Australia and Southern Africa, we have the highest streamflow variability compared to elsewhere in the world. So this presents significant challenges because for us to actually get the same secure supply, we have to build bigger storages to help manage this high interannual variability. But the very things that are causing this high interannual variability is also the thing that allows us to have some reasonable predictability. So this comes under the ENSO streamflow or ENSO rainfall teleconnection. Again, that relationship is strongest in Australia and in Southern America. So we can exploit that relationship and the antecedent conditions to help forecast streamflow or water several months in advance that will help us to overcome or manage our high variability. And the other point is at a map at the bottom, which shows the rainfall elasticity of streamflow. So that number is about 2 to 3 in Australia. What this means is, as a general rule of thumb, you can say a 10% change in rainfall would translate to about a 20 to 30% change in streamflow here in Australia. So this amplification of rainfall change in the runoff is also higher here in Australia compared to elsewhere in the world. So this has ramifications in the context of how changes in future rainfall might impact on future streamflow. All right, zooming into Australia now, if you focus on the map on the bottom left, so that really shows the runoff distribution across the country. So most of the water is generated up in the north, in the tropical north. But it's very hard to capture the water because most of it occurs in a monsoonal season. And the soils there, also leach a lot because of the high runoff generation. So they're not really conducive to strong agriculture in that region here. So most of the development in Australia is happening in the east coast and also in the southeast. And in terms of having a look at the hydroclimate characteristics in recent years, the biggest thing is the rainfall decline in the rainfall trend that you see over much of eastern Australia and southwest Australia. And this drying trend is amplified in the stream. So the plot on the top shows a time series of inflows into the Murray River system. We're all too familiar with the millennium drought over the last 10, 15 years, 1997 to 2009. So very dry conditions, unprecedented dry streamflow during that period. Of course, what we are seeing in the southeast, we have already seen that in the southwest, where since the 1970s, there's not a single year in record that we had an inflow into the Perth Reservoir system, which is bigger than pre-1970 averages. So much so that in terms of water management in the southwest, all they're doing is just using records post-1975 to represent the design period to decide how to manage the water resources system. Okay, and there are reasons that we believe are causing some of this. So the plots on the left-hand side shows changes in the last 30 years in the warm season and in the winter or cold season. So you have a look at the warm season at the top. The last 30 years has not been anything magical. In fact, some parts have been a lot wetter than elsewhere. But you have a look at the cool season at the bottom plot. The southwest and large chunks of eastern Australia, we have the driest 30 years in record there. So a lot of the decline in streamflow that we're seeing is really caused by the decline in this cool season rainfall, which has persisted even after the millennium drought. And our climate scientists or climate colleagues have shown that there's some anthropogenic signal in some of this decline in cool season rainfall. A lot of it is caused by what we would expect in a warmer world, causing the expansion of Hadley cell and pushing the winter storm tracks further south, missing the southern Australian landmass from Perth some 40 years ago, starting and possibly starting in the southeast here. And we can see that in a strong correlation with global temperatures, with the blocking highs represented by the South Tropical Ridge. So we are starting to see more of that more happening and strengthening with time. It's interesting also to note that the global climate models, which are highly uncertain and even the direction of rainfall change, particularly in summer, as shown in the plot at the bottom right. In winter, you find that in this case here, percentage of global climate models from the latest CIMIC 5 or IPCC 5th assessment runs, pretty much all the models or large proportion of them are showing declining winter rainfall across large chunks of Australia, particularly in the southeast and southwest. So there are these multiple lines of evidence that points towards we got a drying winter happening, and because most of the runoff or water in the south parts of Australia are generated in winter, so less winter rainfall translates to less winter runoff. If all the runoff is happening in winter, that results in likely declining future water availability in the southeast and southwest. And we can do all these projections as I've shown here, using a combination of global climate models, downscaling methods, and hydrological modeling. But there's big uncertainty in the estimates. So these numbers have been available since 5 years, 6 years, maybe even 10 years ago. If you have a look at the north, you've got a very large range in the projections of what might happen to runoff for 1 degree global warming, where significant changes can happen, but they range from a big decline of say up to -20% to +20%, with median value of about no change. So it's very hard to manage given this kind of big uncertainty in the system. But if you focus on the top plots again in the far Western Australia, even the wettest range of the projections is showing a decline in your future stream flow. So there's a likely decline in the southwest. The question is how much, ranging from -12 to -37% in this case here. And likewise in the southeast, even the wet projections show little change there, all the way down to about decline of 20% in your stream flows. So these numbers, like I say, have been available for some time now, and water resources agencies and other sectors do use this to adapt, and there's some adaptation that has already happened in the water resource sector for several years now. So I'll show some examples here, but really focusing on the water reforms that's been going on in the Murray-Darling Basin, where the government has spent $12 billion to upgrade irrigation infrastructure, improve irrigation water use efficiency, and purchase what amounts to about 2,500 gigaliters of water for the environment, and setting up new sustainable diversion limits for all the catchments. I wouldn't say that it is climate change alone that caused a lot of these things to happen, but a lot of water reforms is underpinned by, we know we have had significant overuse or overlocation of water, and this is a lot of the reforms have been brought forward, and I suppose triggered by that, as well as the millennium drought and projections of drier futures. So here just are some examples of policies and investment mechanisms, like on-farm investment to improve irrigation water use efficiency, reducing losses in irrigation water delivery, and enhancing irrigation water use to improve technology and knowledge and water buyback for the environment. So it's not just these policy mechanisms that help, there are other operational mechanisms that also help us manage to dry periods. And one example is the adaptation of irrigated agriculture to water trading. In fact, Australia leads the world in how we do water trading. So during the millennium drought, although we got a significant decline in water, and in fact, as shown by the blue bar there, we have used 70% less water during the millennium drought. But that has only resulted in 20% reduction in agricultural return, simply because we have moved through water trading to shift water to higher value used. So that's just an example in the Murray-Darling Basin. So there are things and mechanisms that we're doing to help us sustain to longer dry periods. Having said that, there's no question that the volume of water that has been purchased back for the environment, that 2,500 gigaliters or so I mentioned, that volume is very similar to what we are projecting, the decline, the median projection of decline in water in the Murray-Darling Basin. So because of this, a lot of the buyback could possibly be wiped out by declining water from climate change alone. So we need to find better ways, or we need to maximize, we need to do better at maximizing value from water used. So some of the things that are heavily in operational space, application space, as well as research space, indicated by the dot points on the right. So trying to establish a more robust knowledge linking ecosystem health to climate hydrology and other drivers to guide, to inform how we can provide water for the environment. We can also take advantage of climate water information. And here, our own Bureau of Meteorology actually leads the world in terms of water information and water intelligence. And one of the useful things from there is possibly the streamflow forecast, which will help us to operate with the systems better and possibly to deliver water better to the environment. So maximizing the use of water in light of possibility of dry conditions in the future. But regardless of what we do, I think at some stage we still need to do some trade-offs or further trade-off between consumptive water use and environmental water use. And possibly, if we continue to have drying projections, we might have to decide on relative value of environmental assets and choose possibly some of the higher value assets to protect or to sustain into the future. So that's just an example from the Murray-Darling Basin. I can probably sit here and talk through examples in pretty much many jurisdictions across the different states of Australia. And I've just chosen one example because of work that we've done in the state of Victoria through the Southeastern Australian Climate Initiative and in the Victorian Water and Climate Initiative that's happening now. So these predictions are being used by catchment management authorities, by water utilities, by stakeholders across Victoria to come out with water strategies and water demand and supply trends to cope with dry conditions, as well as potential decline in future water resources. So I might pause there and just flick this onto the screen because this represents possibly the latest projections that we have put out and published, and the numbers are available. So what I've shown on the screen here are projections of future water availability or projections of changes in streamflow, in median streamflow for the time slice 2046 to 2075 relative to the 1976 to 2005 period for RCP 8.5. So RCP 8.5 represents the high end of projections, high end of emission scenarios. And all these numbers here probably relate to what might happen for about 2 degrees Celsius global warming compared to the pictures I showed you earlier, which is about 1 degree global warming. So these numbers are comparable with the earlier numbers multiplied by 2, I suppose. This one is further in the future or for higher emission scenarios. But largely they tell a similar story where in the north, we are a lot less certain about what might happen in the future. But certainly in the southwest and southeast, if we just focus on the runoff plots, you can see that even the wet end of projections do indicate a decline in the southwest or little change in the southeast. But across the whole country, yeah, we got a projection of median projections of largely decline across the whole country with significant declines in the Southeast Australia and far Southwest Australia. These are pictures for long-term water availability or for long-term averages, but it's important to note that we can do this easily, but it's a lot more difficult to robustly provide projections of changes at the tails of the distribution, and a lot of time it is the tails of the distribution that we got to manage for. So here are some examples where in Southeast Australia, we might be talking about multi-year drought in terms of storages and irrigation. In the inland areas or where environmental flows are important, we are looking at both sides of the spectrum, so the low flow end as well as floodplain connectivity at the high flow ends. In cities and coasts, we might be talking about flood hazards. We're hearing more and more about the Great Barrier Reef, and this relates more to the high flow events, generating sediments and impacting on the water quality, impacting the Great Barrier Reef. And we are also hearing a lot about potential for sustainable infrastructure development in the north. And here we got to deal with monsoonal rain and water capture in the north. So a lot of the impact are not just long-term averages. Also, although it is a good surrogate, it is also being able to derive future projections of these water metrics at the tails of the distribution to help make smart policy decisions and sustainable adaptation in the notion of dry periods and climate change. So it can be confusing with the different metrics. It can be confusing with the different projections that are available out there. So a lot of these, I think, has to be done in close partnerships or close communication with the stakeholders so that we can ultimately tailor the projections for whatever it is going to be used for and work directly with the decision makers to make informed decisions in terms of policies, in terms of management and adaptation options in water resources and sectors. So what I'll do now in the second half of this talk is focusing on some of the science challenges from the hydrology perspective. So a good picture to start it off is really this slide, which I tend to show to depict the different components that we got to think through and go through when we think about projecting future water security and water availability. And with each of these components, there are all kinds of sources of uncertainty in these components here. So on the left-hand side relates to the emission scenarios. So you hear all these terms commonly thrown around, RCP 2.6, 4.5, 6.5, 8.5, and so on. So RCP stands for Representative Concentration Pathway. So that's a means of how the IPCC uses it to depict what might the different emission scenarios moving in the future. The numbers simply represent the radiative warming at the end of the century, by the year 2100. So 8.5 represents a business as usual type thing. 2.6 represents a condition where we virtually stop emitting greenhouse gas. And 4.5, 6.5 is probably more from all the way from the Paris Accord to a bit more higher emission scenarios. And obviously, there's time horizons. Further in the future, we see bigger changes, and in the near term, we see less changes. But in some way, I tend to think of these as whatever we do, you get the warming. It's just a question of how much and by when. And likewise, in terms of a runoff or rainfall, in places where you're projecting a drying, what the drying will happen again is just how much and by when. So a lot of the hydrology part of the story, from water part of the story, a lot of the future projections depends very much on the future rainfall projections, and that's just simply a very wide range, a big range of uncertainty in the future rainfall projections. So a lot of the traditional methods of using to do these projections, we tend to use material coming out from the global climate models, and a lot of projections that you see out there are actually projections coming out from the CIMIP-5 models or relating to the IPCC AR5. In the next 3 or 4 years, we are going to see more CIMIP-6 models coming out to coincide with the cycle of the IPCC 6 assessment report. And we are also getting more and more of these downscaling products, which is using the boundary conditions provided by these global climate models to provide higher resolution projections. So that's the opportunistic space that we'll be moving on into the future. But suffice to say, there'll be a lot more of these projections coming out. So it's very complicated for even the researchers to work out which ones to use, how to use that, and how to make sense of all these projection data sources. Now, I'll refer you to last month's webinar, which is put together by Michael Gross, and that's really a good place to start thinking, start having a look around what we are going to try to make sense about these projections in the coming years to deliver the next gen climate projections. The good thing is there's a coming together of researchers in this area. There's a wantingness to actually be able to make sense out of these and provide guidance on, given all these different projection data sources, what's the best way to think through that, and which are the best sources to use for whatever applications we might be choosing to do. So again, I refer you to Michael Gross's presentations from last month's ESCC webinar. And what I'll do here for the remaining of my talk is focus on these two aspects to complement Michael's talk on looking into two features that we got to overcome from a hydrological perspective. The first one is how we work with modifying or adapting the rainfall projections for hydrological simulations. Again, more and more we are going to use projections that's coming out from the high resolution dynamic downscale type rainfall, but there's a lot we got to do to actually modify the rainfall or bars correct the rainfall so that we can sensibly use it for hydrology. And the second bit is really how we go about extrapolating our models to predict a future that is controlled or that will be very different from what we've seen in the past, given that we're using a lot of past information to develop our model. Okay, I'll just show some examples of why we need to bars correct for the rainfall for hydrological applications. So this plot here, I'm trying to show here the observed rainfall patterns in this plot here. In the middle plot here, I'm showing the rainfall patterns that came out from WRF, which is a typical downscaling, dynamic downscaling regional climate model. This is not necessarily the latest simulations from there, but typical simulations coming out from that, using the reanalysis data to provide the boundary conditions. And this plot here simply shows the same historical simulation from the downscaling, but using the global climate model. In this case here, the ECAM5 global climate models as the boundary conditions. So if we compare this plot and the observed plot, these are the bars of error that I'm talking about in terms of the mean annual rainfall. Now we start having a look at the future rainfall coming out again from the WRF downscale from ECAM5 boundary conditions. So that is this minus this here. You're seeing these differences in the changes in future relative to historical rainfall. I've plotted all these on exactly the same scale. So what you're seeing is the changes that we're talking about here is actually smaller than the bars that we are seeing in the data. So that's just to provide context about the kind of error correction that we are applying to be able to use that for hydrology. Having said this, despite the bars here, despite the differences between there, we can always force that to look exactly the same by using bars correction with a non-parametric or parametric method, and we do that. And this is what I'm trying to show here in this plot here, where if you just have a look at rainfall coming directly from the boundary conditions provided by the reanalysis data, the blue lines, the blue dotted line is the raw data that came out from the WRF model. Now, we can always bars correct, and we have done that to force it to look exactly like the observations. Now, even when I do that and apply it to streamflow, I can't reproduce a streamflow. And in fact, what I find is I will always underestimate the streamflow collectively coming out from the bars correction. So that compares this number, even after the bars correction 166, and that's an underestimating the observed flows of the 2 to 7 in that case here. And the reason for that is, despite trying our best, the downscaling methods simply do not sufficiently preserve the day-to-day rainfall correlation. And I'm trying to show it here through the probability of the wet-to-wet transitions. And again, these are observed data. So these are the results from bars corrected reanalysis data or bars corrected with boundary conditions provided by the historical, by the global climate model, by the ECAM global climate model. These two pictures are a bit less blue than that, and that's the error we're talking about. So despite the bars correction, we're still underestimating the wet-to-wet day transition. In fact, what we're doing here, we are underestimating the cumulative sums of multi-day rainfalls, the 2-day rainfall totals or 3-day rainfall totals that generates runoff. And because of that, we're seeing these errors still in the downscale data. And across the state of Victoria, from work that we've done with the Victorian Water and Climate Initiative, this leads to underestimation of runoff when we use bars correction, which doesn't take into account the day-to-day rainfall correlations. So that's just one example from a need to bias correct downscale rainfall for hydrological modeling applications. I don't have the time to talk through the other dot points, but I hope I've given you a flavor of many things that we got to do the adjustments before we can actually use the rainfall data to drive hydrological models. The next two dot points talks about the need to maintain the spatial correlation, and the third dot point relates to when we are bias correcting at the different scales, we do get different numbers. So we got to make some decisions over whether we are talking about trying to preserve the changes depicting by these downscaling methods at what scale, at what temporal, and what spatial scale. Okay, I'll focus on the other dot point now, which relates to what we need to do with hydrological models to be able to predict future water futures. So this is just a plot trying to depict that the model streamflow projection can be influenced by the choice of hydrological models and the parameterization used. So I'll try to go through these. So what I'm showing here are the ranges of change that I see from 286 catchments across this part of Australia, southeastern Australia. Let's just focus on sensitivity perturbations on the left-hand side plot, where perturbed by a 10% increase in rainfall, and see what might happen to the mean annual stream flow, the high flows, and the low flows. I've used three rainfall runoff models here, GR4J, SimHide, and the Jinanjiang model, and the colors represent what would happen if I actually parameterize or calibrate them all to reproduce the daily flow simulations in black, or to reproduce the high flow simulations in blue, or to reproduce the low flow simulations in red. So when we're looking at a mean annual stream flow, I probably get quite good agreement regardless of which model I use and how I go about calibrating the model. But when I start looking again, I was talking about a Taylor distribution earlier on. If I'm looking at the high flow characteristics or the low flow characteristics, the results do matter on the choice of hydrological models and do matter on how I parameterize the models. So there's some work that needs to be done by hydrologists in figuring out what might be the most optimum approach for the different applications that we might want to use the models for to make future hydrological projections. The other problem we have encountered is this thing which is now called hydrologic non-stationarity or hydroclimate non-stationarity, and it's a parallel problem of we train our models using data we have, but when we apply our models to predict for a different period, which is very different from the period we train, we simply don't do as good a job, or possibly do a very bad job even. So what I've shown here in the left-hand side are the relationship between runoff and rainfall for these catchments in Victoria. Each dot represents one of those, all these represent the different catchments, and the dots represent the data across the time period I have. I'm just simply plotting the annual runoff versus annual rainfall, and plotting the line of best fit through it. So the red dots that you see are what happened in the runoff and rainfall during the millennium drought. So you can see in quite a few of these plots, the runoff rainfall relationship is actually below the line. So you have a different runoff relationship. You don't expect a model that you have built using the past data to be able to reproduce that. The thing is, we don't see that in all the catchments. You see that in many catchments, but some catchments, like the ones here and here, do not exhibit that relationship. So we got to find ways of how we trick the models or parameterize the models better to be able to reproduce a prediction in a period that is different from what the period that we use to train the model. Now, there's been a lot of research and ongoing research using this data set as a test bed, because we are one exemplar situation where you got this significant decline in the rainfall causing an even more significant decline in the runoff. As one exemplar test data bed, I suppose that globally you could use it. Not many parts of the world we've seen this kind of characteristic over that longer period. And this is an active area of research by ourselves and a lot currently by the University of Melbourne, looking at what might drive some of the influence. What are the influence of this thing that's causing us not to be able to simulate dominant hydrological processes during long dry spells. So I've shown some examples here that during the millennium drought, which is shown in this dotted line here, you know, we got relationships between runoff and rainfall, which looks, well, whatever, looks normal over the past. But during the millennium drought, we continue to have rainfall which is slightly lower, but there's a lot of, in this particular catchment, runoff, the runoff coefficient turned out to almost zero in that case here, and also depicted here, as well as when we have a look at the cease to flows over the course of the drought. This catchment just had a lot less of the rainfall becoming runoff and a lot of cease to flow conditions, and we believe some of it has to do with the connection between your surface and groundwater. So we saw significant declines in the water table at that time too, and that means you need a lot more rainfall to happen to wet the soils, to cause groundwater recharge to happen, to replenish the water table, so that you re-establish this connectivity between your surface and groundwater system. And we're finding that many catchments just recover differently. And as I said, I mean, there's active research at the University of Melbourne trying to figure out what drives this, so that we can incorporate these processes into our hydrological models. So just to sum up the bits of the top there, it's really about challenges around how we extrapolate hydrological models built using the past data to put into future. So the two drivers are the different rainfall runoff relationships and dominant processes under different hydrologic regimes, and we have to extrapolate a model to warmer conditions that we haven't been using to train a model, and certainly higher CO2 conditions, and with it come feedbacks in eco-hydrological processes and water use, carbon water cycle, not seen in the past data that we use to tune our model. So the modeling solutions include, you could go and build the perfect landscape hydrological model. I think it'd be some way before we actually do that. So in the interim, we need to find a better understanding of what these processes are, and then conceptualize the dominant processes in long dry spells, and maybe do some simple coupling of the carbon and water cycle. And even if we did our best, we probably still need to find pragmatic, fit for purpose calibration and primary approaches. So we still need to do future projections. So how best to do it, how best to trick the model to actually do it, given that we understand the limitations in the models to be able to do its work. Okay, I'll summarize the science bits of this presentation here by saying that when we're looking at delivering projections of water metrics, this stuff on the top right is showing the different components and different considerations that one have to make to deliver future projections of water metrics. Now, a lot of stuff on climate change science and climate projection science is a big component. And again, I refer you to Michael Gross's presentation in last month's seminar, which talks to that and how Australia is trying to build a consensus approach to how we do better, more robust next generation of projections. And what I've shared with you today is really the part around the bias correction for hydrological applications from the hydrology side, and how we train models to be able to more robustly predict projections for water futures under change. And from the climate side of the story, there's a lot of work done in the NEPs, as well as the next gen projections, which Michael Gross spoke about. From the hydrological projections, there's a lot of work funded by the different states, as well as the Bureau of Meteorology have an initiative to deliver some of these hydrological projections consistently with how the next generation of climate projections might be delivered. Okay, but regardless of what we do, you're going to find that we know a lot, but there's also a lot that we don't know. So anything that we want to adapt in the future, it will always have to be an adaptation under uncertainty based on current best science or current knowledge. So any adaptation that we do need to consider, the resources, rewards, the actions you take. You might adapt, nothing happens, you probably wasted your money or reacting too quickly. At the same time, if you don't, the risk, the consequences, you might have to suffer the risk and the consequence from that. So it's really using this knowledge to work out the risk-reward consideration of how you adapt the systems, whether it be to incremental or transformational type adaptation. And more globally, we have been articulating the approach around bottom-up decision scaling type approaches to explore system resilience. And if you do these, you really are using this approach to to explore adaptation options, not only to climate change, but also to other drivers. So here's just an example that I'll indulge myself trying to explain that we are starting to work in the Upper Murray. So looking into how one might consider the resilience of the systems. So for example, if I'm interested in ecosystem conditions or whatever, and somehow I can reduce that to a score like this little 73, it's not a single score type thing, but if it was something like a 73 or whatever, I can say that if the way I'm operating the system now, that's the value I'm getting from how I operate the system. And because I'm doing simulations through it, I can tell in this case here that the two biggest drivers is changes in your annual stream flow and changes in your dry spells. Now I could perturb and do a whole series of sensitive studies and probably work out that, you know, under this much change, a combination of change in annual stream flow and dry spells, you know, I might get a condition. This might be a contour showing when a system falls below say 50 compared to 73 because I got drying conditions and less minimal stream flow. I could also put through projections of what might happen in the future. There's about 100 dots there, 100 red dots there, and I can tell that if I was operating this way, well, there's 10 times or 100, 1 in 10 chance that I'm actually falling down below resilience that I'm prepared to adapt in that system. I can now start playing with ways that I can actually operate the system, perhaps to maintain a high resilience, and maybe I can find a point like this where instead of operating the system optimally at a 73, I'm operating the system optimally in conditions of 68 or 100, but I'm operating in this space here where the system is a bit more resilient to decreases in stream flow or longer dry spells. Of course, I can move the system even further if I were to spend money doing infrastructures or maybe buying more water back, but that requires societal decisions, start taking political decisions around how we use our water. So I think I'll finish there and just summarize the talk. And hopefully I've shared with you some of the future hydrological projections for Australia. We know that the southwest and southeast are likely to be dry in winter. Most of the runoff in these regions is generally winter, so that leads to projected decline in future water availability. But there's a large range of plausible projections. I've shared with you some numbers around projections in rainfall as well as stream flow into the future. So I see some of the science challenges in producing next generation projections include combining and interpreting future climate projections from different data sources. Again, Michael Gross's talk last month covered that. From a hydrology perspective, I think the big opportunity is being able to use the high resolution downscaled data, which are becoming more and more available from many sources. But we need to find ways to best correct the rainfall, particularly the rainfall inputs for hydrological applications. And we have to play around with models too, learning how to adapt the models to predict under the future under changed hydrologic regime and under warmer and higher CO2 conditions. I think I've shown some examples, and really there are varying levels of adaptation to climate change in many sectors, including water resource sectors. But it's very important that we combine the science together with the stakeholders directly so that we can translate and communicate the best information, I suppose, to guide policy decisions and to guide adaptation in the water resources and related sectors. I might finish there, Sonia.
Great, thanks Francis. Thanks a lot for a fantastic presentation. Just a reminder to quickly pop down and write some questions for Francis in the chat box as you have some. We've got a few coming through, so I might just read them out to you, Francis, and then get you to respond. So the first one from Nick, he asks, has anyone taken this water availability data and tried to work out its future economic impact, GDP, revenue at a state-by-state level?
I haven't seen any directly, but I wouldn't be surprised if there'll be some desktop studies looking at that. So I haven't seen any Sonia, and I haven't seen any Sonia. I haven't seen any Nick where direct a number associated with it. But certainly at the different sectors, having a look at the implications about water per se, implications about agricultural productivity, yield, and various things. I can't say I've seen something that converted it directly to a generic overall economic cost. But the nearest to it, Nick, I might refer you to, you might Google the Australian National Outlook, which is what CSIRO did, of which this was a small input, one component of many components looking into the kind of futures across the different sectors that one might choose from using some of this information.
Fantastic. And we have another one from Etan who asks, what are your thoughts on the use of AI, machine learning, deep learning, etc., to provide better simulations of rainfall and runoff?
Yeah, I would say that a lot of these are semi-AI related. So it's a combination of the domain knowledge and computing. So that's virtually what we do. A lot of stuff that we understand hydrology is through looking at historical climate and streamflow data, as well as other sources of data, like remotely sensed soil moisture, remotely sensed evaporation data, and it's really putting this data together and learning the processes, including catchment experiments and so on. Once we understand that, we build models to describe that, and we use these models to predict what might happen in the future under changes in whatever conditions, including climate change. So better and better computing technology and better synthesizing of data would certainly help. And we use a lot of computing technology to tune models, to calibrate models, to parameterize model, to actually understand what drives what. So I would say that AI is it's already being used. It's really how we use that together with the domain knowledge to further the knowledge and further to make the models more robust.
Great, thanks, Francis. Well, we haven't had any other questions coming in, so you've got a couple more seconds if you've got a deep and burning question for Francis. In the meantime, I might just thank Francis very much for your presentation today, and also give a little bit of a plug for next month's Earth Systems and Climate Change Science webinar, which will be on the topic of Australia's national climate model, the Australian Community Climate and Earth Systems Simulator Access. So stay tuned for that, and invitations and reminders will be sent out to that in the future. Well, we don't have any other questions coming in, Francis. You must have been crystal clear and very comprehensive. So we might just leave it there and give you all an early mark. So thanks again once to Francis, and thank you all for attending, and we hope to see you at future Earth Systems and Climate Change Hub Science webinars. So thanks a lot and see you later. Bye.
Thank you for listening.